is Professor Mingmin Zhao. He has done some really amazing work at the intersection of sensing, mobility, and I would really put the third category as creativity. I mean, you have professors who actually put a lot of, math and take the theory ahead, but he has applied it in really, really interesting places and looking at essentially uh, wireless communication and electromagnetic waves in a very different way, right? So how we can actually look through walls, how we can actually process these signals. So this is in some sense, what is happening at the cutting edge of sensing and mobility is computing, but also you can think of it as well, if you're really creative and you know the maths, then this is what you can get to. So please welcome Professor Mingmin Zhao.
Thanks, Zhao. Thanks, everyone. I've talked to a couple of you. My name is Mingmin Zhao. I'm an assistant professor in CIS and with a secondary affiliation with ESE. I'm very happy to be here, share some of the recent research that's going on in my group. Basically, today I'll be telling you, how we can use radio frequency signals. I hope many of you in the ESE program might be very familiar with, but today we'll be looking at them at slightly different aspects. We'll be looking at machine learning and how we can use machine learning to actually enable some capability that we humans don't have. So let me start this by saying, basically many of you probably have worked on robots, from this TinyML course or some other courses, in your program. Basically robots, they're everywhere. Like there's market analysis showing, how the number of robots, the market size is continue to grow, in the next couple of years. However, robots, kind of like our human eyes, those sensors, they actually don't see through fog. They don't see through smoke or other, adverse conditions. The good news here is radio frequency signal. Think of your home Wi-Fi or radar on the car. They actually can send signals that traverse through all those occlusions, those airborne particles. Imagine, even if you put your access point in a different room, you will still be able to access the signal and surf the internet. So what we're trying to think of here is, can we use, radio frequency signal to perform sensing or to gain clear vision? Now, unfortunate thing is, despite all those interesting development, exciting development in autonomous vehicle, in mobile robots, many of those robots actually primarily uses visual sensors like cameras and LiDAR. And that got us to think, what is the reason why, radio frequency signal or RF-based sensors are not being used in those latest developments? And what we believe the reason is actually the limiting and coarse imaging resolution of those sensors. Basically, when radar were used on the car, it has been used there for multiple decades. But what they were used for is sort of like for speed measurement, for 1D measurement, detecting there is an obstacle and detecting how fast you're approaching that obstacle, but not really as an imaging device to show, a camera-like image of your surroundings. And those are some of the, state-of-the-art RF imaging system, appear at some of the top conferences. And you can see, instead of seeing, millions of pixels, what radio frequency captures is really just a blob of reflection, very low resolution. And some of the mapping results as a result, is far away from the resolution you can get from visual sensors. Here is another example. Basically, when you put a radar in front of the car alongside with a camera, you can get millions of pixels. You can clearly see what's going on, the object, the tree, the occlusions, everything there. But with radio frequency signals, you don't see any of those. What you get is just blobs of reflections or, after some processing, a sparse set of point cloud. So what we're trying to do, what I'll tell you actually as a result, is we're trying to enable sort of X-ray vision for robots. Like imagine a robot that has this million pixel type of imaging capability, while at the same time being able to see through fog, see through smoke, basically see clearly even in conditions that traditional visual sensors would fail. And I'll first tell you the first system, basically it's a panel radar. It's a RF imaging system that actually gets LiDAR comparable resolution. Basically, it will process radio frequency signals. Through its processing, it will get a range of outputs from range images to surface normals to semantic segmentations and object detections. Basically, all those tasks you traditionally do with images using computer vision algorithm. Now we'll achieve the same thing, but with RF signals, and even in cases when there's occlusion, when there's smoke and dust, etc. So how can we achieve this? A key design, in our system to overcome the limited resolution is to have a rotating antenna. Basically, what you see here is a vertically placed antenna array. Basically, small sets of elements that is vertically placed. What we will do is we'll be using a step motor, something you see very frequently in your computer, fan, server. You see all those motors that is rotating. Here we'll be using this motor to rotate this vertical array. And as a result, while it's rotating, what it forms is actually a very large synthetic array. Basically, let's say here, it's 8 by 1200 while it's rotating. So basically, this rotation allows us to form a 8 by 1200 synthetic cylindrical array. And what is really nice about this array is it turned out that this is actually critical in achieving high imaging resolution. So let me explain to you what I mean by this. So basically, for a single antenna, it's not like a laser or like a pixel in the camera. It actually doesn't form a very narrow beam. It doesn't send out a laser and a beam and receive its reflection. What it does is actually sends a pretty wide beam as the one that is shown here. Then this is the fundamental reason why RF signals have very coarse resolution, because it doesn't have very good directionality. It's not focusing on a very specific direction. It rather actually combines measurements from all this area.
Maybe you can give them some orientation as to what you mean by RF. Because they know about Wi-Fi, Bluetooth, ZigBee, and maybe a little bit of LiDAR, radar, not more than that.
So yes, so that's basically radio frequency signal. If you think of the spectrum of electromagnetism, radio frequency, is the wave that is from a few gigahertz, hundreds of megahertz to hundreds of gigahertz, like millimeter wave. They're also roughly in the range of radio frequency signal. Basically, Wi-Fi, Bluetooth, those are communication protocols that leverage radio frequency signals. And radar here, it also uses radio frequency signal. It's just that the signal is constructed or sent out in a slightly different way, so that it's optimized for sensing as opposed to communication protocols. Communication protocols, you can imagine, it will send wave, encode the packages, encode the data bits to share the data. Here, we will be using them to perform the sensing task.
And these are in gigahertz?
These are 60 gigahertz. So it's millimeter wave signals. And that the reason we want to use those millimeter wave signal is we want to have a relatively compact size for the room. Like many of you, I don't know how many of you have seen those old TV, has gigantic antennas. Those are, with lower frequency, but the downside of those is, in antenna design, the size of your antenna is sort of proportional to your wavelength. So if you want to go with very low wavelength, you'll end up with big antenna arrays. But here, choosing millimeter wave, we can use a relatively compact size of the sensor. Okay, coming back to this array imaging, the nice thing is that by combining multiple of those antennas together, it actually would allow us to form a very narrow beam. Basically, this is a concept of beam forming. I can, let me briefly explain to you what is the core concept behind beam forming. So how many of you have heard or used beam forming, this term, before? Okay. Okay, that's good. So basically, I'll start with a very simple case with two antennas. So let's see, we have two antennas here. And they are sort of form a linear array. And what happens is that when we have a signal that is coming from let's say this is some radio signal that transmits towards those two antennas. But what happens is that if you compare the propagation path they will have to travel along, you realize the signal has to travel like extra distance here to arrive to the antenna on the left, comparing with the antenna on the right. And this distance, let's say the spacing between them is S, this angle of arrival is theta, the additional distance becomes S times cosine theta. So this is what happens, when you have array with spacing, and when they receive signals, there will be some delay in the system. Similarly, if we have a larger array, 3 antennas, n antennas, you can actually know the additional delay the signal will have to experience when it's arriving at different antennas. And with this, what you can do is that you can actually combine the received signal to estimate where it comes from, right? If you have two and you know what is the delay, you can actually go back and calculate where the signal might be coming from. Like in a lot of the video conferencing tool these days, it actually have an array of microphone, those sound bars. If you have seen those in any of the video conference room, it actually can steer the cameras towards where the sound is coming from. It's using very similar concept. And here we sort of extend the concept to a 2D array. What I've shown on the board is basically a 1D array that you can estimate where the signal might be coming from. Here with this 2D cylindrical array, you can do similar things, but you can form a beam that is narrow in both dimensions. So this is what I mean. Basically, we can actually digitally steer the beam along both dimensions, along both azimuths, means that it can scan from left to right. Similarly, at the same time, we can steer the beam vertically, so we can steer it up and down. So basically, this allows us to actually, scan all the 2D directions and form a high resolution panoramic 3D images. This is also using the original capability of radio signal. Original signal, it can measure distance. Now we add the ability for the robot to scan all the 2D angles freely, and combined with the distance measurement, it actually forms a high resolution 3D image of the surroundings. And so far, this algorithm would work well when the robot is static. Here, if the robot is sort of in a corridor, you can see from the LiDAR and from the RF image, you can see the rough shape of the corridor, the corners, the edges, the pillows, etc. However, this becomes a problem when the robot started to move. So here, we have this robot and this rotating antenna. You probably can see there's a black 3D printed case that holds a millimeter wave board that is rotating. This is basically the cylindrical ring virtually created from this rotation. What happens when the robot is moving is that it actually causes distortion. Basically, if you look at the imaging result while the robot is moving at different speed, it actually bends the corridor, which is, of course, not accurate. So what causes this? Actually, the reason is something I just described. It's because of the wavelength we're operating at. Basically, to perform coherent combination of those antennas, to perform this beamforming very accurately, we would actually need very precise location of the antennas at sub-wavelength level. And because we're operating at millimeter wave, this means that we need precise antenna location at sub-millimeter level, which is actually very difficult to achieve. And when the robot started to move, even it's moving slowly along the way, it's actually creating location changes in location that is larger, way larger than millimeter level. And if those motions are not accurately captured and correctly compensated, this is what you'll get. You'll get distorted imaging result. And if you can think of, there are plenty of sensors on robots that is trying to characterize and capture the robot motion. For example, there's IMU, there's well odometry, all trying to design to capture either acceleration or how far a robot has traveled. But unfortunately, none of those sensors, they're able to give you, sub-millimeter level accuracy. And so how can we solve this issue? It turned out that there's a very interesting effect in the signal that actually leads to the solution. So basically, many of you probably have heard this word Doppler effect. If you have a train, a vehicle, coming towards you or coming away from you, the frequency of the sound you hear is not purely, the frequency of the generated sound, but there's a Doppler effect caused by the motion. If a vehicle, if a train, sound source is moving towards you, the frequency sounds higher, and it's moving away from you, the frequency appears to be lower. And what we do is we actually leverage the Doppler effect in the radial reflection to capture them. Think of, while the robot is moving, it is listening to its own reflection from the wall. But by measuring, how this reflection or Doppler effect, it can actually try to characterize its own motion. But there is one issue with the Doppler effect is that Doppler doesn't really give you the full velocity information. So if you look at this graph, think of a robot speed, let's say is v here, and there's a delta theta, that is the direction between the robot moving direction and the direction of the reflector. So when you look at Doppler speed, or what Doppler speed measure is actually a projection of it. It's the visual speed along the observer's direction. Basically, S would equal to v times cosine delta theta. What we wanted to know here is, the original v, but with a single Doppler measurement, it tells us just a projection of it. So how can we, resolve this ambiguity? So the idea here is actually very simple. If we cannot get the full answer from a single reflector, what will happen if we have multiple reflectors? And naturally, when a robot is moving around the environment, there's naturally multiple reflections from different sides, different chairs, different objects, tables, etc. So what happens with multiple reflectors is that, let's say for a single reflector, we get Doppler speed measurement. We don't know where exactly, the full speed vector will be, but we know it's somewhere along this line, such that its projection would align with this S1 measurement. Okay, but then with the second Doppler measurement, we know the full speed is somewhere along this line. And with each of those lines, we cannot fully determine the speed, but with two of them, and by looking at the intersection, that actually helps us to resolve this ambiguity. And this is, of course, just the case with two objects. In natural environment, we'll definitely have more than two. And we have developed some methods that actually combines Doppler measurements from objects from all 360-degree, and then use that to estimate the moving direction accurately. So here is how the system works. So think of, while the robot is moving in this V direction, let's consider all the reflectors from 360-degree while the robot is scanning. What you will realize is like all those reflections, they all satisfy the same equation, which is S time equals V times cosine delta theta. And all those Doppler speed measurements, while we're looking at different azimuth angle, they form this sine wave. It forms a curve. And what we can do is we can do a sinusoidal curve fitting, and that tells us two parameters. The amplitude of the signal tells us the full speed of the object, basically magnitude of v, while the initial phase of this cosine curve tells us delta theta. So by doing this cosine linear fitting, we can know the full information where this robot is heading and how fast it's moving along that direction. Okay. And unfortunately, that's not the full story. There is another caveat in measuring Doppler effect or in capturing accurately the Doppler information. So basically, if we were, to have a full array, a full cylindrical array, and that array is moving towards an object, we can accurately get Doppler effect and angle of arrival. Angle of arrival is what we use to do beamforming. But unfortunately, with a synthetic array, what happens is that while our robot is moving, we are scanning different directions. Those are not actual physical antennas. Those are synthetic ones. And what happens is that we are leveraging those different antennas to do beamforming, but at the same time, when we measure Doppler, we look at the reflection from a single antenna over time, which again happen to be those 5 antennas. And this creates an issue because both the angle of arrival information and the Doppler information, they are all mixed together as part of this spatial frequency. And what we need to do here is we actually need to decouple the angle of arrival and the Doppler so that we can accurately do the compensation and do the image. And I'm not going to get into all the details of how we address this, but a high level intuition is actually fairly simple. Now you think of a radar that is rotating while there's a single object. And what you can do is you can track the reflection in the reflected signal. And here is what it will look like. While the robot is focusing on different or scanning different directions, the spatial frequency that we observe is changing. Initially it wasn't in the field of view, so it's very weak. As the object gets into field of the view of the robot, it becomes stronger, and then decays again. An interesting observation or intuition is that each of the objects will have the strongest reflection at the moment the beam is directly facing the object. It's basically the peak of this reflection. And this peak is also very interesting because, as we said, this peak happens when the radar is facing the object. That means the angle of arrival at this point is 0 because it's directly facing the object. And at this point, we will know the corresponding spatial frequency. It measures fully the Doppler effect. So what basically this is what we need to do is simply identifying the peak on each of those lines. And those will give us the pure Doppler effect without the angle of arrival impact. And here is basically the full picture. If we look at all the signals from objects in the environment, here is what it will look like. This is actually some signal we have captured from the robots. You can see the center of those peaks sort of falls along the sinusoidal curve. But at the same time, each of them has a spread due to the angle of arrival and Doppler coupling. But what we can do here is we can simply detect the peaks for each of those lines and then perform the same sinusoidal curve fitting, and that can tell us the speed information of the robot. And then we can go back and look at the beamforming equations and slightly revise it so that we, instead of using, assuming all the antennas are on the cylindrical array, because the robot started to move, those small motion, those small changes in the antenna location can be taken into account by simply adding the, velocity information. And that will, recover or address the distortion we saw earlier, which allows us to do accurate imaging. Okay. So this is basically, the first step of the imaging. We use signal processing to understand the robot motion and use beamforming or compensated beamforming to do high resolution imaging. So we carefully analyze the imaging resolution in the system. And what we ended up finding is that with our antenna setup, we have a pretty good range resolution of around 3.75 centimeter. That means, along distance measurement, it has an error less than 4 centimeters. And then along the azimuth angle, it has a resolution of less than 1 degree. So this is fairly good, similar to what you get with a camera or LiDAR. But unfortunately, one limitation of our system at this point is its elevation resolution. Depending on the size of the radar, we have an 8 by 1200. This vertical one actually becomes a bottleneck. With 8 antennas, what we were able to get is around 14 degrees. So it is not too bad, but comparing with the azimuth resolution, it's not as good. It's not going to be able to give you, image like or million pixel type of range images. So what the idea we have here is, why don't we leverage machine learning to enhance the vertical resolution? The intuition here is that, spatial dimensions, they are not independent. Like if we have high resolution along the horizontal axis, a lot of those information can be transferred to the vertical dimension. I can give you 2 examples, surfaces that typically continuous in the 3D space. Think of stairs, floors, or walls. Like knowing the exact position of them on one dimension actually helps you to estimate the other dimension or enhance the resolution of the other. Similarly, for indoor environment, there's always gravity constraint, right? You cannot have a trash can floating in the air. It needs to have support. It is to be standing lying on the floor. Similarly, for human, for other objects, the gravity constraint, all those information are telling us those 2 dimensions are not independent. And the best way, for us to capture those dependency and the correlation between those dimensions is to use a data-driven learning-based method to enhance the resolution. And a naive approach, you can try to address this problem is to use, 3D convolution, right? Our input is 3D signals, like with range, azimuth, and elevation angles. And then our output might be a 3D point cloud. So it's a 3D input and 3D output. You can think it's pretty natural to use a 3D convolutional neural network to do this. But there are actually two issues with the 3D component. The first issue is that 3D convolution are pretty expensive. But to train, to run inference, it's not that efficient. The second issue is that if you directly try to learn the point cloud, think of as a classification task, which points in the 3D space are occupied at the point versus the position that doesn't have one. It's kind of like a classification task, right? Predicting whether it is occupied or not occupied. But you quickly see that it's actually highly imbalanced classification because only a small number of points are actually occupied in the 3D space. Vast majority of the points, they are actually not occupied. So this sparse point cloud makes it also difficult to do this binary classification. And what we ended up doing to actually make it a lot more efficient is to reformulate this problem as a dense regression task. So instead of trying to predict 3D point clouds, what we do is we use this 3D heat map and try to learn a range image. So what is a range image? Basically, think of a panorama range images. It's kind of like what you take with your phone. You rotate your phone 360 degree and naturally stitches together. Here we have a similar image. This is actually a corridor, and you can see two ends of the corridor. They are 180 degrees away from each other. And this theta and phi just tells you, which angle it is. And the value of the pixel here tells you the distance along that angle. Basically, how far you have to go to reach the first reflector. So that's what is range image. Very similar to the panoramic image you take with your phone. Is that now it doesn't encode RGB value, it encodes depth. So to do this dense regression, what our model will do is to take this 3D heat maps as input while treating the range dimension as channels. And then without using 3D comp, we actually can do it more efficiently with 2D comp. And it's also easier to train, easier, faster, way faster to do inference. And with this, we can get a pretty accurate range images, similar to what you would get with a LiDAR. And this allows us actually to unlock a wide range of visual recognition tasks, similar to what you would have done with the images from camera or LiDAR, except that now we can do it with radio signal in the presence of cloud, fog, etc. For example, we can do surface normal, we can do semantic segmentation, we can also use faster RCNN type of architecture to do object detection. And this is how we actually implemented the system. My student, built this whole robot platform and has a millimeter wave radar rotating on a step motor. And this is the mobile robots that you can use a joystick to move around. And this is a top-down view of the robot. Basically we use a JSON nano to stream to do the computation. And on top of it, of course, there is a 3D, like a $10,000 3D LiDAR that was used as a ground truth reference to evaluate and to train the model. And this is some data set. My student, they actually, to build this data set, they travel around the whole Penn campus. They entered some building I've never been to. There are 12 buildings with very different style. And they told me, when they actually look up on the Penn website to see what the year those buildings were built, they actually spend the whole century. Right? I think that's one nice thing about Penn, very, very long history. We have buildings that's, over 100 years old. And we were able to collect, very different style, very different material, building structure, etc. Basically, we use that to form a data set that allow us to train and validate our algorithm. So what we do is that we do a sort of a leave one building out test. Out of those 12 buildings, every time, what we do is we train on 11 buildings and do the testing on the remaining one, basically to ensure, we're testing in a new environment. And we repeat this process 12 times. Every time, a building is sort of acting as an on-scene new environment, while the model is trained on the remaining 11. And to evaluate the system, what we look at first is the range imaging accuracy. So what we can do is we can compare the output from our system and compare it with the LiDAR. If you look at LiDAR, you notice there is some white dots. Those white pixels basically are the places where there's no reflection. Basically, LiDAR say, oh, I cannot tell the distance. I cannot measure the distance along this direction. But what we can do is we can compare them and we can calculate per pixel error for this range estimation. And this is the CDF plot of the error distribution. You can see that our system panel radar actually achieves a median error of 3.4 centimeter, which is pretty accurate comparing with LiDAR. And as I mentioned, we did this, repeat this test 12 times, and you can see the error is actually consistent across all those 12 buildings. And here are some of the detailed images, captured from panel radar, and we put it alongside with the LiDAR. And you can see the system was able to capture all those fine-grained details, including the stairs, the chairs here, and also the human standing in the corridor. And here is another visualization when the robot is moving in the corridor. You can see the different objects, chairs, trash cans, person being detected, and semantic segmentation, floor, ceiling, door, wall, chairs on the floor, and also at the same time surface normal as well. The nice thing about this system is that the robot actually has many aspects that can actually outperform traditional cameras. And it's particularly interesting in this case. It actually outperformed the supervision or supervisor. Think of this training strategy as kind of like a teacher-student network. Teacher is using LiDAR while the student is trying to perform the same task, but with radio frequency signals. And one common scenario that camera struggle with is glasses. Think of a robot moving in the indoor environment. If it cannot accurately detect glasses, it might just run into the glasses and cause all sorts of problems. And this is because lights, actually they can easily go through glasses and doesn't capture any reflection. And if we put the LiDAR here, it actually doesn't see the glasses, it actually sees the object behind the glass. At the same time, with radio frequency signals, they actually do reflect off the glasses, the material, and that can perform, accurate imaging, even, the vision cannot see them. And here's another scenario. It took a lot of effort to shoot this video. Basically, the first time my students set this up, they bought a so-called fog generator on Amazon, and they told me that they claimed they wouldn't trigger the fire because it is fog, not smoke. And what happened is that 30 seconds after they turned it on, there was a fire now. And then they have to evacuate the whole building. I wasn't there. I was actually at home. It was Saturday midnight. That's the first time, my PhD student called me on the weekend midnight. And I was very surprised. And then they were calling me, asking me what they should do. They accidentally triggered the fire. And later, that's why we built this, tank, so that the fog, or I don't know whether it's smoke or fog, sort of limited insight, so the fire alarm would be happy with it. And last week, we brought this whole setup to DC at a conference, and we did the real-time demo there, and we got like multiple awards, best demo, student research first place, etc. So what happens in this? Let me play it again, actually. So what happens here, you see, as my students adding the smoke or fog into the tank, you see the front camera is sort of getting blurred. Similarly, for the LiDAR, it started to tell you a lot of white pixels. This is because it doesn't, see through the smoke, and it's tell you, oh, there is no return. I cannot tell you the depth of my surrounding. As the fog is getting thicker, the LiDAR, it's completely white. It's not telling you anything useful at this point. While the radio frequency sensor, RF sensor panel radar, still rotating inside, it's still covered accurate corridor structure, no trace of person, there's some objects on the floor, etc. Okay, so that's That's basically UPenn radar. So we have the code and the data set all available on the website. If you are interested in learning more, you can visit the website and play with the code and the data set. So screen sharing. Okay.
I have a question.
Yes. Any questions?
So most of what you've shown was like indoor environments, rooms with hallways. How do you test it yet, like in an outdoor environment, maybe rooms like foliage or things that are like kind of like more solid than smoke,
Mhm.
where it's like not like permeable, but like would obstruct the view. Like have you tested it?
Yeah, that's a good question. Actually, part of our demo is we also did some thick material, paper, curtain, all those things. It easily go through there. But that's a good question. Actually, for example, the drywall, millimeter wave would have a difficult time going through. And if you want to, have better penetrative capabilities, you want to go slightly lower frequency. You see some of that firewood uses, 5 to 10 gigahertz signal that is around 6 times, 5 times lower frequency. We're able to see through the drywall. It's kind of like you think of your home Wi-Fi. The wall doesn't really block it, just attenuate a little, but doesn't completely block it.
But if you were to lower that frequency, would you have to then go and change the models that you use?
The model, yes, you probably need to tweak it a bit, but I don't think that's the biggest impact. I think the biggest downside of going to a lower frequency is, let's say, if we make the frequency 2 times lower, our setup will have to be 2 times bigger. You think of those antennas, television, right? Because they want to travel very long distances, they use lower wavelength, and then you get gigantic, those dish type of antennas. So, I mean, I think sort of it's a trade-off. You want a larger sensor versus better, capability of going through occlusions.
I guess one thing I was curious about was like, I mean, we're operating at the like gigahertz frequency, but the actual rotation of the sensor is like orders of magnitude slower.
Mhm.
Like, how are you still able to get like a decently good, like I remember like the cosine graph with the like diagonal line, like how do you get like decent resolution even if the antenna is rotating so much more slowly? Like, do you have to tune that carefully or?
Not really. So I think those two are sort of independent. Like basically our motion will never be as fast as speed. Basically, as far as the speed of the light, like electromagnetic waves, they travel at the speed of the light. So there's no way we can be reasonably close to that. So and also in actual modeling, it doesn't cause any issue. If you think of all the speed measurement, the place, detecting your speed, whether you are overspeeding on highway, they don't need to be moving close to the speed of light to be able to tell this. They can even be completely static and measure the speed.
Okay, so is the only thing you need to know like positionally exactly where the antenna is? Is that all you really need to know to do it accurately?
Yes.
Yeah, think of it as a template, right? So like a speed radar needs to be like that Nyquist, it should just be more than 2x the speed of like. Fine.
So I guess we're almost
Yeah,
up for the time, right? Maybe I can quickly show, there's something, we actually extended this to do slim. So think of a robot that is driving around the building. We're actually able to capture not only a single range images, it actually able to reconstruct the high fidelity mapping of the environment. I mean, I think I'll just move to a quick video, show you what the system was able to achieve. I don't know, many of you might be familiar with where this is. Anyone know where this building is? This is actually more. This is the second floor of the more. You see this interesting.
Yeah, with the
You
stairs.
come up on the first floor and then this is, I think, we are probably here
Yeah.
right now. Yeah.
How do you fix that?
So this is like different
You're
buildings.
not used to seeing it in that view.
I think this is the Vin building.
Okay, that's why.
This is the Vin, you have this like student space in the middle with chairs, etc. Yeah. Yeah, my student asked me this. I think that stair structure was the sort of the signature of the Moore building. Okay, I think with that,
Yeah. Thanks.
sure, sure.
So this gives you like some. So 2 points. One is this gives you like, an idea that, hey, we can go beyond these sensors, LiDAR camera. We can actually just use the whole RF spectrum. And this is using it at, you can sweep through frequencies. You can almost do like an MRI scan for, places, right? You could go through windows, you could go through foliage, you could go through like density, right? You could even like do a scan of a person as you go through if needed, right? I mean, that would be a much higher power system, but it's just telling you that now your palette is much richer. The second point is Professor Mingmin does like amazing work. His lab is just downstairs, opposite the Deadkin lab. And ever interested in working at this intersection of sensing and machine learning, please reach out to him.